Okay, what we're going to be working on today is mainly how all the other numbers inside of the parent function, how it works with shifting around the graph. Now, a lot of times, the equation has to be it has to be set up in a very special way in order to use the transformations. Having a parabola or a quadratic equation set up in standard form doesn't work with the transformations. We have to have it set up in vertex form before any of that stuff works. But if it's set up correctly, then transformations makes it a lot easier in order to graph things. So what we're going to be doing is working with what the transformations are and what they mean. So I set it up first. If you have your parent function, then this is the generic form of the general function for any of our parent functions. So what I'm going to do is I'm going to kind of write down what each of the letters mean, and then we'll go through and we'll do examples of graphs with each of these in there. So to start off with, let's start with the easy ones. What does H do? Now, if I add or subtract a number to the x value inside of an equation, it shifts it horizontally. So what we're looking at is something that looks like this. So the f of x may be messing you up, but that's what we're looking at. So if the f of x is referring to a parabola with the x squared value, if I'm subtracting something from the x, this would be my h. So what does the k do? Yeah. Okay, B, you guys don't, in Algebra 2, if your teacher mentions it, it's kind of glazed over quickly. But, so let's skip down to A real quick, and then we'll talk about B. What does A do? So if I put a number in front of the x value, I don't think I got to an example like that yet, but let's say that I have something like 5x squared. Or negative x squared. What does that do? Yeah. If I have a negative, it flips it over, right? If I have a 5, if I put a 5 in there, what does that do? That shrinks it down, correct? So if I had like a parabola that looked like this, and I put a 5 in front of it, it would squish it down. If I put a 1/2 in front of it, it would spread it out. What's a good way of... Yeah, let's do speed. I like... it depicts how quickly you're going up or down. I never liked saying stretch and squish because, that's... What?
So the bigger the number, the closer it's going to be?
Yep. So the bigger the number, the faster your points go up. The smaller the number, the slower they go up, so the more stretched out it looks. Yeah. So it's like slope. If I put a 5 in front of it, it's going to go up really fast, so it's going to look squished together.
So you're saying the bigger the number, the skinnier it is?
Yeah. So it's kind of like slope. B does the same thing, it just does it horizontally. So we're going to get into the horizontal a little bit. We're going to save it for second semester mostly, because we're going to really get into it second semester where we're doing our trig functions. But I'm going to introduce it briefly right here, mostly for the direction aspect. But it comes into play a lot more with our trig functions. All right, so graphing. What I'm going to do, it really doesn't matter what we use for parent functions. So just so we don't have to go and redo this for every single parent function, I'm just going to stay consistent. I'm going to do this for x squared. And I'm lying a little bit because for the b, I'm going to switch to square root. So where we get to where I want to talk about the b, I'm going to switch parent functions on you. But I wanted to start off with something that you were very familiar with. So x squared you guys have been doing since Algebra 1. So I've just wanted to start with something you were familiar with and would feel a little bit more comfortable with. All right, so to start off with, if I was just graphing x squared starts at 0, 0, right? And I'd have the point 1, 1, and 2, 4. 1, 2, 3, 4. And then if I was really desperate, I could go out to 3, 9, but I'm not that desperate for a point. Negative 1, 1, and negative 2, 4. So this is my parent function. So I wanted just to have that to start off with so we can see how it's changing each of our graphs. In the past, I've tried putting the little dotted graph on each one of them, but that seems to cause more confusion than doing any good. So I'll just make a base graph to start off with. All right, on example 2. What is my h value? 3. So remember, since my equation has a minus sign in it, this is saying x minus what value? So I'm actually subtracting a positive 3. So pretty much anytime we see anything in parentheses in pre-calc, there's always a minus sign in there, so we always use the opposite value. So if this would have had a plus sign on it, we would be using negative 3. So my k value is what? Close. Negative 2. Because this one actually had a plus sign on it. So this one I used the actual thing. Okay, so this means I'm going to move my graph where? How far? Right 3. Right 3. Because it's positive 3. Nope. Well, it is backwards from the way it looks in here. This looks like a negative 3. And then down 2. So my point was originally at 0, 0. So now my vertex is going to be at 3, negative 2. 1, 2, 3, negative 2. So there's my new vertex. Okay, now there's two ways of doing this. You can take every single point and move it 3, -2. So I could take this point at 1, 1, and I could go 1, 2, 3, 1, 2. Or you can know what the graph looks like, and you can just draw your graph off of your vertex. So I know from this vertex that my other points are over 1, up 1, over 1, up 1, and over 2, up 4. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. That's the benefit of knowing the parent function. And that's what I'm going to be challenging you to do. Especially when we start working on A's and B's, that's what I want you to try to do, because that's what makes it easier. That's the benefit of using transformations. Not trying to move every single point, but moving your central point and then graphing off of that central point. Okay, so from there, I have my graph. They weren't random, right? I know from my base graph that from here I go over 1, up 1, over 1, up 1. So that's my vertex. So I'm graphing off of that. Okay, so for example 3, let's just do an A value. I'm going to go kind of, I don't know. I'm trying to match going slow and going fast because I don't know where all of you are based off of that first thing I had you do. Some of you are a little advanced, some of you are a little not advanced. So bear with me. I'm trying to balance this so that we all end in the same spot at least, or close to the same spot. Okay, I'm gonna do this version of it twice, and I'm gonna show you why, because some teachers teach this incorrectly. So I'm gonna start off. I'm gonna teach this how other teachers teach it, and then I'm gonna do another example and show you why these teachers taught it to you wrong. It'll work for this one, so we're all good. We're good this first time. I'm not going to do a problem wrong for you. We're never going to do that. Okay. So I'm going to start off. I'm not going to teach you incorrectly, but A is sort of like slope. We can always use it as slope for your first point. So I can always treat this like -3 over 1. For my first point in each direction. Well, sort of in... Actually, I shouldn't do that. For first point to the right. After that point, you have to know what the graph looks like in order to get the rest of your points. Okay, so I start off at 0, 0 for this graph, right? So to get my first point, I go -3, 1. So over 1, down 3. 1, 2, 3. Now, knowing what a parabola looks like, I know that's mirrored on the other side. So here's my other point. So that can give me my parabola. Okay.
How many points do you want to have when we're the problem?
You can have 3. I'm happy with 3. If you give me that much, that's enough.
The ordinary great ones?
Yes. Now, Let me go ahead and expand on that a little bit and tell you everything that does. What A actually does is in all your ordered pairs, it takes and it multiplies all of your y values by A. So you know my other y values like 2, 4, I didn't graph that because that's going to go to 2, negative 12. That's where that one goes to. So that's a little bit more. So that's why it only works as slope on the first one, because since our order pairs are squared, it doesn't act linearly after that first point. Okay, you good with that? Yeah. You can, but we want to move past that. Yes, you could. And that's what I would suggest. If you, on a test, don't leave something blank. If you get stuck on the test, it's better to get some points. You can always plug in numbers. And you always fall back on that. You know, the very first way you learned how to graph was to plug in numbers. Always fall back on that if you forget how to do anything else. So, I mean, the whole point of this is I want you guys to learn how to do transformations, but never forget the basics if you forget how to do your new stuff. Okay. Now, let me show you why that's wrong. Not wrong, but not totally correct.
Wait, the way you did that?
Yes. I didn't give you all the information because that's how some teachers do it, because that's how some teachers understand it. And then, you know, you do it on a test, and you may do it, and then I'm going to count you wrong because you did it incorrectly. And then another teacher may count you entirely correct for the way you did it. And that would make me so upset.
So you don't want the teachers to if he gets to do this to get back to how you do it?
I want you to do it correctly. I want you to have the correct answer. And just to let you guys know, I have a master's in math. I know what I'm talking about. I don't even have a degree in education. I don't have a teaching degree. I have a math degree, I have a bachelor's in math, and a master's in math. I don't have any education degree at all. I went through a transition program to get I have a license to teach, not a degree to teach. I'm licensed by the state to teach you. I have no college degree to teach you.
What you're saying is
Yeah, I'd have to go to another state and get a license to teach. Okay. What?
Are a lot of teachers like that here?
No.
Like, you don't need
No. Most teachers have a degree. And actually next year we're going to be in trouble as far as offering the college credits because there's only 2 teachers at this school who have a master's, and next year they're only letting teachers who have a master's degree in math offer it for college credit. So we're going to be in trouble because I was planning on not teaching math next year at all. So I may not be able to actually do that. I may have to still teach this. Okay. Okay, if you would follow what I did last time, let me show you how this is incorrectly done, and some of you may have done this in the past. If you follow what I did last time, some of you may start off this problem and go up 1 over 2 and put a dot, because I told you to do this like slope, right? That is incorrect. And a lot of teachers will tell you to do it that way and will count it correctly if you do it that way. That is wrong. The problem is, it only works whenever you move over 1 space. That is the kicker. It only works as slope whenever you move over 1. That is the only time it works as slope. You have to move over 1. So in order to use this as slope, this is how it works as slope.
So, 1 over 2. So
Huh?
1 over 3.
What?
That was all of them?
Yes, that's with all of them. What?
So it would be up 1 over 3.
No, it would be over 1, up 1/2. Yeah.
If we were stubborn and just put A over 1 all the time and you graph it like that, would you kind of wrong?
No, you should put A over 1 all the time. All the time. That's how it has to happen. You cannot go up 1 over 2. That is incorrect. That is entirely incorrect. If you try to do that, if I went up 1 over 2, that would put my point right here at 2, 1, right? Plug 2 into this.
2.
If I plug 2 into that, I get 4. Half of 4 is 2, right? Well, this says I should have the point at 2, 1. You just told me that I should have a point at 2, 2. So that just tells me that what I just did is incorrect. Yeah, John. It only works going over 1 because the whole idea that whenever you plug in 1 into something, you usually get itself back. That's the quality of 1 that lets that work. Is that wherever you multiply by 1 or divide by 1, you get itself back. So in order to make this work, this is where we would be. Because remember, whenever we do this, we should be taking all of our y values and multiplying them by a, right? So originally, my ordered pair here was 1, 1. So if I take half of that, I should be at 1, 1/2. At 2, 4, if I take half of that, I should be at 2, 2. But again, if I followed the slope thing, I would give an ordered pair at 2, 1. So if you were taught that before, I am so sorry that you were robbed of your childhood.
Can you explain that again?
Whenever you use the slope idea, it only works wherever you move to the right 1. So it's always your slope is like